Okay, so let us start. It is already past 3. So, welcome to the ninth session of this Advanced Engineering Mathematics course. So, the main concept that will be in use today are elementary probability theory. So, I hope the screen is visible. So, if not, please let me know, and please follow this pointer. I hope you can see it. Okay. So, okay, in this week's assignment, there was a problem on discrete Fourier transformation, but I will not be discussing that because that is pretty straightforward. So, if you know the algorithm, you can just simply use that. So, there is no subtlety involved actually. So, that is why I decided to discuss only on the probability problems. Okay, so for that, so the probability problems that have been given in this week's assignments are actually pretty elementary. So even if you don't look at the lectures that has been delivered this week, the problem still can be solved using the concept from class 12, I think. So that's that. So today's problems will be very easy. Okay, so let us start. Okay, so the first problem will be the one. So there are 4 machines, and importantly, it is known that exactly 2 of those machines are faulty. So I have highlighted this thing. So it is known. So that is actually very important. So there are 4 machines, and we know that exactly 2 of them are faulty. Now they are tested one by one in a random order till both the faulty machines are identified. Okay, so 4 machines, they are tested one by one till both the faulty machines are identified. So find the probability that only 2 tests are needed. So to identify the 2 faulty machines, so as can be seen by common sense, so at least 2 tests are needed, and of course there are only 4 machines, so at most 4 tests can be needed. So number of tests needed can be 2, 3 or 4, and out of that we have to find the probability that only 2 tests are needed. Okay. So, and now this is very important to note that this thing. So it is known that exactly 2 machines are faulty. Okay. So since so what will be the scenarios? So only 2 tests are needed. So only 2 tests are needed if the 2 tests identify both of the faulty machines. That is one scenario, or both of the functioning machines. So yes, so if the 2 tests identify the 2 faulty machines, then we are done. That is fine. But if they identify both of the functioning machines, we are also done, because we have identified the functioning machines, and we know that there are two faulty machines, so we don't need to perform further tests to identify the faulty machines. Okay, because we have found functioning machines, and we know that the remaining two must be faulty machines. So that is why I have underlined this. So it is known, it is quite important. Okay, so these are two scenarios. So probability of finding the two faulty machines in two tests is this. So in the first test, what is the case? So if the first test picks up a faulty machine, that means we can choose four machines. So out of four machines, we can choose two machines. So two are faulty. So that is the probability. So the probability of finding a faulty machine in the first test is 2/4. Okay. And after finding a faulty machine in the first test, the probability of finding another faulty machine in the second test will be 1/3. Because now one faulty machine remaining, and out of the remaining three machines, of course one faulty machine remaining, and the probability of drawing that one faulty machine is 1/3. So the total probability of finding the two faulty machine in two tests is, you multiply this and you will get 1/6. So that is that. And now we have to consider the probability of finding two functioning machines in two tests. Okay. Similarly, the probability of finding the two functioning machines in two tests is given by this. So in the first test, you can draw between four machines, and two of them are functioning. So drawing a functioning machine in the first test has the probability of 2/4. Okay, and having identified one of the functioning machines, in the second test we can find another functioning machine with this probability 1/3, because now during the second test, machine remaining is 3 and functioning machine remaining is 1. So that is why this is 1/3. Okay. Multiply them and you will get again 1/6. Thus, as I said, so there can be two scenarios when both of the tests identify faulty machines, or both of the tests identify functioning machines. So we have to add up these two scenarios. Adding up these two scenarios, the total probability that only two tests are needed is this. So add up 1/6 plus 1/6 and you will get 1/3. So that is our final answer. Okay, another thing I need to mention is that this question occurred in the previous year's assignment problems, but the correct answer was given as 1/6, but it should be 1/3, as I have just shown you. Because this 1/3 will be because of this phrase. So it is known. So we know that exactly two of them are faulty. Since it is known, so that is why this second scenario of finding two functioning machines in two tests also count as this, that only two tests are needed to find the two faulty machines. Because as I said, once you have identified the functioning machines, the remaining two must be the faulty ones, as we know from before. So that's that. So now moving on to the problem 2. So this will be our problem 2. So a person answers each of two multiple choice questions at random. So I have written that as MCQ. So he have to answer 2 MCQs, and there are 4 choices for each MCQ. Okay, so he has 2 MCQs, and there are 4 choices per question, and moreover the person answers the question at random. So he randomly chooses one option out of 4 for every question. So we have to find the conditional probability that both answers are given, both answers are correct, given that at least one is correct. So it is a conditional probability that is little different. So given that given that he has correctly marked one answer, at least one answer, so what is the conditional probability that he has marked both the answers correctly? That is the question. So let us start. So the probability that both answers are correct is, of course, so answering question 1 and question 2 are 2 independent events, right? So there is no relation, there should be no dependence between answering MCQ 1 and MCQ 2. So answering them are 2 independent events. So the probability, the corresponding probabilities have to be multiplied. So the probability that both answers are correct is this: 1/4 multiplied by 1/4 is 1/16. Because of course you know out of these 4 choices only one is correct. So that is why the probability of correctly answering a question is 1/4. Okay. So this is the probability that both answers are correct. And now the probability that at least one answer is correct is this one. So at least one answer is correct. This is the, what do I say? So this is actually complementary to the scenario that both answers are wrong. So as you see, so both answers are wrong and at least one answer is correct. So these two, if you take the intersection, so that includes all the possibility in which the questions can be answered. Okay, so at least one answer is correct means it already has these 3 scenarios. Like, so the question 1 is correctly answered, but question 2 is wrong. Also, question 1 is wrong, but question 2 is correct. Or question 1 and question 2 both are correct. So at least one correct includes these 3 scenarios. And the 4th remaining scenario can be that both question answer 1 and answer 2 are wrong. So these are the 4 scenarios that can occur in this problem. And thus answering at least one correct and answering both answers as wrong is 2 complementary situations. So that is why this. So the problem that at least one of the answer is correct is 1 minus the probability that both answers are wrong. Because as I said, so this scenario, this scenario that at least one is correct and these scenarios that both answers are wrong, these two are actually complementary situations. So that is why if I know probability of one scenario, then I can immediately tell what the probability of of its complementary situation is. So you have to just minus 1 minus that thing. So that is what I have done. So the probability of answering both questions wrongly is this one. So 1 minus 1/4. So 1/4 was the probability of giving correct answer, and 1 minus 1 by 4 is the probability of giving wrong answer for one question, and similarly for the second question. So this is the probability of giving both answers wrongly. Okay, and then the probability that at least one is correct is this, because that was the complemented situation. So 1 minus probability that both answers are given wrongly, and that is why the answer is 7 by 16. Do that. And now the conditional probability that both are correct given that at least one is correct. Okay, so this is the formula for conditional probability. So the conditional probability that both are correct given that at least one is correct is this. So this is the formula. So the probability that both are correct divided by the probability that at least one is correct. So this is the formula for conditional probability. So the conditional probability that both are correct. So what you have been asked to find answer to what you have been asked to find the probability of that should be on the numerator, and the thing that is given, like here given that at least one is correct, so the known thing should occur in the denominator. So the probability that at least one is correct is in the denominator. So divide and you will get 1 by 7. So this is the answer to this question. Okay, so let us now move on to the third problem. So a computer uses two programs, A and B, 40% and 60% of the times respectively. So 40% of the time it uses program A, and 60% of times it uses the program B. Okay. Now, if the program A is used, there is a 75% chance that A will run before its time limit is exceeded. Okay. So if A is used, so there is a 75% chance that A will actually execute the problem it was called for. Now for B, the chance for this occurrence is 50%. So 50% of the time B will run before its time limit is exceeded. Okay. Now for a random problem, it is known that the time limit has been exceeded. Now we are given that the time limit has been exceeded. Now with this knowledge, what is the probability that B was used? Okay. So we know that the time limit has been exceeded. Now what is the probability that B was used? So in this kind of problems, we actually use the Bayes theorem, but I will present it in a form that you will not actually need to memorize Bayes theorem, because if you try to memorize the formulas, there will be much more formula and you will be overwhelmed. So it's better to understand the strategy and the language. Okay. So let the event that runtime limit is exceeded be E. So I denote this event as E, mind you. So this E event is that the runtime limit has been exceeded. Okay, and in the question we were given the success rate, we were given the complement of this event. We were given the probability of the complement of this event. Okay. Now the thing, so let the events that the program A was used be A, and that the program B was used. Okay. And the program B was used be B. And you see, so there is only two programs, A and B, and that means using B means that is the complement of the situation when the program A is used. That means the event B, which denotes that the program B has been used, is actually complementary to the situation that when the program A was used. So B is actually a complement. So in this case, in this problem, this is the case because there are only two scenarios available. So either use A or B, and using B is like A complement, and using A is B complement. So just that. So now in the question we are given that the computer uses the program A 40% of the time. So that means probability of occurrence of the event A is 40%. That means probability of A is 2 by 5, and probability of B, the remaining thing, the probability of B is given as, so in the question it was given that B, so the program B is used 60% of the times. So that means the probability of occurrence of the event B is 3 by 5, because this is 60%. And you can simply check that this 3 by 5 is actually 1 minus PA, and that also verifies our intuition that B should be A complement. So PB is 1 minus PA, and 1 minus PA means probability of A complement. So that is the definition of A complement. Okay. So we have just verified that B is actually A complement. Now probability, now we have to find the probability of this event E. So now we have to find the probability that the runtime limit has exceeded. So how can that happen? So there are usually two scenarios. So these two scenarios are this. So probability of occurrence of the event E is that when program A was used and the runtime limit was exceeded, and or, so there is this and or, you have to be very careful while using them. So there are two scenarios how the runtime limit can be exceeded. So one of the scenarios is that program A was used and the runtime limit was exceeded, or the another scenario is program B was used and runtime limit was exceeded. So these are the two scenarios, and you have to add them because they are two mutually exclusive scenarios. And now this is the probability of the event E intersection A. So E intersection A means that both E and A has occurred, right? And E union A means at least E or A has occurred. So intersection means and, union means or. So this is the English language interpretation. So intersection means and, union means or. So here E intersection A, that means program A has been used and the runtime has exited. Okay. So, and the formula for this thing is this. So this is the formula for intersection events. So probability of E intersection A is equal to probability of A multiplied by probability of E given A has occurred. So these things were covered in the lectures. I hope you are familiar with this. So this is the definition. This is actually the definition of the conditional probability. So the conditional probability that E has occurred given A has already occurred. This is P conditional probability EA multiplied by PA gives P E intersection A. So this, and similarly for the second term also you have to use the definition of conditional probability. Okay, and why are we using the conditional probability or this definition of conditional probability here? Because that because that is what is given in the question. So in the question, so please carefully look at this language. So this is, you have to look at this language very carefully. So if A is used, there is a 75% chance. So that means there is a 75% chance that the time limit will not be exceeded given A has been used. So this is actually the conditional probability. This is actually the conditional probability of P E complement A. So the conditional probability of the occurrence of the conditional probability of the occurrence of the event E complement given that A has occurred is 75%. That is given in the question. So we have to find the conditional probability of the occurrence of the event E given that A has already occurred. So that is PEA, and PEA will be what? So 1 minus 3 by 4, because 3 by 4 is P E complement vertical line A. So the conditional probability that E occurs given that A occurs is this one. So 1 minus 3 by 4 multiplied by 2 by 5. So 2 by 5 is just probability of occurrence of A. And, sorry. So please mute yourself so I can hear background noise. So yeah, similarly for the second term also. So as I said, so A complement means B. So we have to find the conditional probability of the occurrence of the event E given that B has occurred. And the complement of this, the probability or the complement of this event was given in the question as 50%. So that is why we do 1 minus that 50% and multiply that by the probability of the occurrence of the event B. So which is 3 by 5. So this thing. So add them up, and you will get the probability of occurrence of the event E is 4 by 10. So this is the probability, this is the total probability that the time limit is exceeded. So now we have to find, so in the question we are asked to find that it is known that the time limit is exceeded. So now, given this knowledge, what is the probability that B was used? So again we have to find a conditional probability. So given E has occurred, what is the probability that B has also occurred? This is the conditional probability. Now what do? We use the definition of conditional probability, which is this ratio, the definition, and clearly, so as I have said earlier, so B is just A complement, so I have written that, and then I have used the and to evaluate this numerator, I have again used the definition of conditional probability like this. So we know the denominator right away, so it is 4 by 10 as we have just calculated, and now this numerator, so this numerator is the second term in the summation, right? So you see, so this is exactly the second term in the summation, and that is, and the result for that was this one. The result for that is this one. Substitute this in the numerator and you will get 3 by 4 as the answer. So that is how you solve these problems. Okay, now let us move on to the next one. So the next problem, so you see the previous problems can be solved using the Bayes theorem directly, but as I said, so if you take that approach, you need to memorize a huge number of formulas, so it's better to use this symbolic, these symbols for languages and use just the definition of conditional probability. Now the next problem, again, this problem also can be solved by using Bayes theorem, but I will not do so. So there are 3 coins in a box. So these 3 coins are different from each other. So one has head on both sides, another is a fair coin, and the third one is a biased coin that comes up head 75% of the time. And fair coin means, so it turns up head 50% of the time. And the coin with head on both sides, that means it gives head 100% of the time. So these are these 3 coins. Now if a coin is drawn randomly from the box and that shows head when flipped, what is the probability that it was the coin with 2 heads? So again, the conditional probability. So given that the coin that was drawn showed head when flipped, what is the probability that it was the coin with head on both sides? So we have to find this conditional probability. So now again let's define these events. So let the event of drawing, please look carefully. So this is only the event of drawing but not flipping. So the event of that denotes a particular result of the flipping will be defined separately. So the event of only drawing the coins are defined here. So the event of drawing the two-headed coin be H2, okay, and the event of drawing the fair coin be F, and the event of drawing the biased coin be B. Okay, so these are the three drawing events that can be possible. And you see, the drawing procedure is unbiased. So, of course, so there are three coins, and you can draw each of them with equal probability, and that means the probability of these three events are all equal, and it's nothing but 1 by 3. So equally probable. So you can so drawing of any coin is equally probable. So this, and now I will define the event of showing head when flipped as H. This is that. So the event of showing head when flipped is H. Okay. Now we have to find the probability of finding head when flipped. So this is the probability of event H, that is of showing head. So what is the total probability of showing head? So there are three scenarios, of course, three coins, three scenarios. So the first one is that you have drawn the coin, the two-headed coin, and that has given you head. So and means intersection, as I have said. Then there is the second scenario, that you have drawn the fair coin and that has shown H. Again, and means intersection. And the third one, you have drawn the biased coin, so that gives it 75% of times, and that shows head. So these three scenarios are possible. And now we have to use the conditional probabilities that is given in the question, because you see, so what is the probability of finding head for each coin? So from the question it is evident that it clearly depends on the coin in question. So for the two-headed coins, the probability is 1. So you should frame this statement like, given that I have the two-headed coin, the probability of showing head is 1. So this is a conditional probability. And for the fair coin, this is again. So given that I have drawn the fair coin, the probability of showing head is half. Again, conditional probability. And similarly for the biased coin also. Given that I have drawn the biased coin, so the probability of showing head is 75%. So these are the three conditional probabilities, and we have to use them to find the probability of the intersections. And for that purpose, we simply use the definition of conditional probability. So, okay. So this is the formula. So P H intersection H2 is actually this, as we discussed in the previous problem. So it is the conditional probability of H, given that H2 has occurred, multiplied by probability of H2. So multiply them. So the first one is 1. So PHH2. So this is 1, because given you have drawn the two-headed coin, what is the probability of finding head? So it is 1, and multiply this with PH2, the probability of drawing the two-headed coin, and it is 1/3. So that is that. Similarly for the fair coin, so the conditional probability of showing head for this fair coin is half, and the probability of drawing it is 1/3. And similarly for the biased coin, so it shows it 75% of the time, that is why 3/4, and the probability of drawing is 1/3. Add them and you will get 3/4. Now, so what do we get? So we get that the probability of showing head is 3 by 4. So the head can be shown like this three after these three defined roots and adding them up because they are mutually exclusive. So adding them up and you get the probability of showing head as 3 by 4. Now we have to find the conditional probability. We have to find the conditional probability that given the result is head, what is the probability that we have drawn the coin with head on each side? So a conditional probability, and that scenario is described by this event. So the scenario H2, given that H has occurred. So given that head has occurred, what is the probability that H2 has also occurred? And for that purpose, again, use the definition of conditional probability. Okay. And then you see in the, again, so denominator is known, that is what we have just calculated, it is 3 by 4. And the numerator, what about that? So the numerator is exactly this one, the first term of the summation, and you see the result was 1 by 3 simply. So put 1 by 3 in the numerator and 3 by 4 in the denominator, and you will get the answer as 4 by 9. So that is the final answer. So just analyzing the statement, I mean what is given and what are you asked to find the probability of. Like determining the conditional statement is the main thing. So the problem 5, so this is the most involved problem using this conditional probabilities. So a problem is given to two students A and B. Now we are given some conditional probabilities and some probabilities. So the conditional probability that A can solve it given that B can solve it is 3 by 7. Okay. And then we are given another conditional probability. B can solve it, so the probability that B can solve it given that A cannot solve it is 1 by 7. So this is another conditional probability. Now finally we are given the probability that B can solve it is 1 by 10. So here it is simple probability. So the probability of B solving this problem is 1 by 10. And here we do not consider whether it can solve it or cannot solve it. So for B, the probability for solving this problem is 1 by 10. So now given these three probabilities, what is the probability that A can solve it? So similarly as for B the probability is 1 by 10, what is the probability for A to solve it without any consideration of whatever B is doing? So irrespective of B, what is the probability that A can solve it? Now let us again, so let us first define the events. Let us first define the event that A solves the problem. So this is, so event A solves the problem. Event A bar, A cannot solve the problem. So these are the two events. And now probability of occurrence of event A is PA, and similarly the probability that B solves the problem is PB. So by B I have implicitly defined the event of B solving the problem. So in the question we are given this conditional probability is 3 by 7 because given that B can solve it, the probability that A can also solve it is 3 by 7. So this is the conditional probability, and probability that B can solve it is 1 by 10. This is simply this, irrespective of what A is doing. And the third one is what? Given that A cannot solve it, B can solve it, and this event has the probability of 1 by 7. So B can solve, even A cannot. So this is the third conditional probability. And now, so we have these three equations. So we have these three equations, and from there we have to find PA. I have to find PA. Okay, so let us proceed. So nothing, just the definition of conditional probability will be needed. So let us start for this. So use the definition of conditional probability and substitute the values given in the questions, and you will get this. This is first step. So PA intersection B, and what is this probability? This is the probability of both A and B solve the problem. So this is probability 3 by 70. Okay, and now again use the definition of conditional probability for this case. And one thing is that we are, so in this line, so we have find P A intersection B, and what is PB? Okay. So PB, probability of B solving the problem. So how can it happen? So it can happen in two different ways, like when B and A both solves the problem, and when B solves the problem and A does not solve the problem. So these are two mutually exclusive events. So we have to add these two probabilities. So ultimately what matters is B solving the problem. So probability of B solving the problem is equal to probability of B and A both solving the problem plus probability of B solving the problem but A not solving the problem. So this is that. So we have just found this first term. So this is 3 by 70 as we have just found, and probability of B is given as 1 by 10 in the question. So that means the probability that B solves the problem and A does not solve the problem is 4 by 70. And now from this one we can find the probability. So this given probability. So we are also given this conditional probability. So this is B solving the problem given that A not solving the problem. And mind the difference. And here it is B solving the problem and A not solving the problem. So we have to use the definition of conditional probability again, and I have just taken terms from left hand side to right hand side and interchanged and rearranged things to finally express it in this form. So probability of not intersecting is equal to this ratio. Okay, this ratio, and I have just substituted the values. So we know the numerator, we also know the denominator. Just substitute the value and you will get this result. So this result is probability well, okay. So yeah, so this is the probability of A not solving the problems, and we have to find the probability of A solving the problem. So that is the complement of this event, and that is given by 1 minus A bar. So the final answer is this. 3 by 5 is the final answer. So you see, you just have to analyze the logics, nothing more, and most importantly, understand what is the conditional probability and what and which is not. So yeah, since we are running out of time, so let us keep this problem. Again, this is the logic is similar, just a little more involved. So in this problem, I have skipped all the logic parts and just use the symbolic notations and use the formula, and I hope that you can convince yourself of this solution. Yeah, let us. Okay, and another thing is that here I have found a different probability than the one that is actually asked in the assignment. So please be careful. I have deliberately chosen to find a defined probability or the probability of a defined scenario than the one asked in the assignment. So, yeah. Now this problem number 7 will be involving a little different concept. So this will be the first problem that involves the concept of a random variable. So 5 devices are subjected to successive reliability test. Okay, and we are given one condition. Each device is tested only if the preceding one turns out to be reliable. So like if the preceding one is not reliable, there is no point testing whether the next one will be reliable or not. So that is the condition. Each device is tested only if the preceding one is reliable. And the probability of passing the test is 0.9 for each device. So find the expected number of tests done. So expected number of tests done. So we have to understand, so how many tests are actually needed. So as is evident from common sense, so at most 5 tests can be done, right? Because there are 5 devices, and at minimum 1 test can be done, because whether a test works or not, you have to actually perform the test. So minimum 1 test and maximum 5 tests, and 2, 3, 4 are also possible depending on the scenarios. So let us begin. So let SI denote the event that the ith device passed the test. Okay, so I have denoted this event like this, and this is a simple probability. This is not a conditional probability. It's simple. So SI denote the event that the ith device passed the test. Okay. And in the question it is written that all the device has a probability of 0.9 of passing the test, and that means PSI is 0.9 irrespective of I. Okay, So now probability, let us now start. So now we will find, so we will actually treat the number of tests as a random variable. And as I just said, the number of tests can vary from 1 to 5. So our random variable, so the number of tests is the random discrete random variable that can take values from 1 to 5, and of course, and the number and and for the discrete variable to take different values, there are different probabilities associated. Okay, that is what we will now find. So here, please note this. So let x be the discrete random variable denoting the number of tests. Okay. Now probability of doing one test. So the probability that the random variable x takes the value 1 is what? So that is same as the probability of doing one test. And when do we do one test? So we do only one test when the result of the first test is itself negative. So that means PSI S1 complement. So PS1 complement, that means the first device failed the test. So the probability of it is 0.1. So complement of passing the test. So and when this happens, we do not perform any further test because the first device itself has failed. So probability of doing one test is 0.1. Similarly, probability of doing two tests. So, and this is simply equal to the probability of the random value x taking the value 2. Okay, so this is the same probability. So probability of doing two tests is what? So for that, you have to pass the first test and then you have to fail the second test. Otherwise, if you pass the second test, you will have to move to the third one. So you have to fail the second test to perform only two tests. And the probability for that is 0.9 multiplied by 0.1, and that is that. And why do we multiply this? Because these are actually independent events. So passing of device 1 and passing of device 2 are two independent events. So that is why the intersection probability should be just multiplication of these two probabilities. So similarly, the probability of doing three tests are just that. So passing the first test multiplied by passing the second test but failing the third test. So this is this. Similarly, the doing four tests is that passing first three passing first three tests and then failing the fourth one. Okay. And finally, what is the probability of doing 5 tests? For that, you have to pass all 4 tests. And it doesn't matter whether you pass or fail the 5th test, right? Because whenever you pass all the first 4 tests, then you are anyway going to do the 5th one, and the result of the 5th one doesn't matter. So what is the probability of that? So just multiply this 4 independent probability for these 4 independent events, and you will get the probability of doing the 5 tests. And as I have said, I have defined them as the random variable, the number of tests, and that is that. So Px1 is the first one, Px equal to 2 is the second one, that probability of doing 2 tests, and up to Px equal to 5, which is the probability of doing 5 tests. This is this. And now we have to find the expected number of tests done. So that means x is our random variable, discrete random variable. It can take values from 1 to 5 with these associated probabilities, and given these probabilities and the value of the random variable, we have to find the expectation value of the random variable. We have to find the expectation value of the random variable. So expectation, what is the, so and that will be the expected number of tests. So what is the expectation value of the random variable? It is quite easy. So yeah, just use the formula for finding the expectation value of a random variable, of a discrete random variable, and this is the formula, and you will get the answer as this 4.0951. Simple. And now the last problem of the day. So again, the problem involving discrete random variable. So two distinct integers are to be drawn at random from the first 6 positive integers. So from 1, 2, 3, 4, 5, 6, you have to choose two distinct integers. Let x be the absolute value of the difference of these two numbers. Okay, find the variance of x. So we will treat x as the discrete random variable. And what is x? X is the absolute value of the difference of the two numbers that were drawn. So you see, you have access to the first 6 integers. So 1, 2, 3, 4, 5, 6. So clearly, what can be, what are the values of x? So of course, it can take values 1, 2, 3, 4, 5, right? Because if you, so you have to choose two distinct integers, so that is why 0 cannot happen. So minimum can happen is 1, and maximum can happen is 5, because 6 minus 1 is 5, and that is the maximum value of x. And 2, 3, 4 are also possible. So x is a discrete random variable. So now we have to find the probabilities associated to every values of x. So let me denote the probability of x taking the value 5 as this, p x equal to 5. Okay. So what is p x equal to 5? And there is only one scenario when x can take 5, and that is when you draw 1 and 6, right? And there is no other scenario that will give you 5. So that is the only scenario, drawing 1 and 6. And out of 6 numbers, in how many ways can you draw two distinct numbers? Then that is the 6C2, like choosing 2 from 6 distinct objects. And out of these 6C2 possibilities, you have to draw only one, that is 1 and 6. That is drawing 1 and 6. So out of the 15, so total 15 possible choices of drawing two distinct numbers from first 6 integers, you have to draw precisely one, and that is why the probability is 1 by 15. So 6C2 is 15. So this is 1 by 15. So p x equal to 5 is 1 by 15. Okay. And similarly, p x equal to 4, like the probability of x taking the value 4. So how can it happen? It can happen when you draw 1, 5 or 2, 6. So two scenarios are possible, and those are mutually exclusive. That is why you add them, add the probabilities. So probability of drawing 1, 5 and probability of drawing 2, 6. Add them and you will get 2 by 15. Now probability of x equal to 3. So there are three possible scenarios. Probability of drawing 1, 4, probability of drawing 2, 5, probability of drawing 3, 6. So three scenarios, so 3 by 15. And similarly, as you can easily convince yourself, Px equal to 2 is 4 by 15 because there are 4 ways that x can take the value 2, and P x equal to 1 is 5 by 15 because there are 5 ways x can take the value 1. So the discrete random variable x can take the values 1, 2, 3, 4, 5 with the associated probabilities that we have just calculated. Now we have to just simply use the formula for mean and variance. So for mean, what do we do? So this is the formula for mean, the average value. This is the formula. Use this and you will get 7 by 3. And what is variance? Variance is defined by this. So expectation value of x square minus square of mean. So this is the variance. So expectation value of x square. So you can easily find that, and then you have to subtract the square of the mean that we have just derived. So do that and you will get the answer as 14 by 9. So that's that. That concludes today's problem session. So